Hey guys, Mr. B here, and in this video we're going to be going over the chapter 11.2 notes on types of chemical reactions. Alright, so we're going to start off by talking about what are the 5 general types of reactions. So the 5 main types we have are combination. Sometimes this is also known as synthesis, so aka synthesis. Though I will always typically refer to it as combination, but you may see synthesis written in other places. We have decomposition, single replacement, double replacement, and combustion. So we're going to go into each of these in particular so we can understand how each one looks and how it works. So a combination reaction, as it sounds, is where we have 2 or more substances that are reacting to combine and form a single new substance. These can either be individual elements that are combining to make a compound, or 2 compounds combining to make a more complex compound, or it could be an element in a compound combining to make a more complex compound. Either way, though, you're typically starting with 2 or more reactants, and you're ending up with one product. Okay? So, the example that they show here in the picture is Mg, and it might be hard to read. It might be a little bit small, so I'm just going to make it bigger here. So 2Mg plus O2, and they're making 2MgO. Okay, so we see that they have magnesium and oxygen, and it's combining to make one new compound, magnesium oxide. All right, so here's an example problem. So it says copper and sulfur are shown in the image, which I just deleted, and they are the reactants in a combination reaction. Complete the equation for the reaction. And it does say 2 reactions possible. All right, so we are going to have copper reacting with sulfur. So Cu, and then it's a solid. Okay, the S in parentheses just means it's a solid. Reacting with sulfur. And there's 2 reactions possible. So the reactions that can happen, and the reason why there's 2. When copper bonds up with sulfur, it's going to make some form of copper sulfide. But remember that copper is a transition metal. And when it bonds with sulfur, we don't know what the charge on the copper will be. It could be +1 or it could be +2. And most likely, it's going to form both. So in the first reaction, we might have copper 1 sulfide, which would look like this. Okay, and the reason why it would look like this is because copper 1 sulfide, we have copper with a +1 charge bonding with sulfur, which is a 2- charge. So we need 2 copper ions to bond with this. Okay, so again, this is copper 1 sulfide. Okay, that could be one product. Otherwise, our other reaction would be copper reacting with sulfur, and we're going to make copper 2 sulfide, which would look like this. Okay, and again, it's going to look like that because now we have copper with a 2+ charge bonding with sulfur with a 2- charge. You only need one of each. Okay, but either way, the 2 reactions that we would have would be either this one. Okay, so this would be 1, or this one. That would be the other one. Okay, so those are the 2 possible reactions that can happen. Either making copper 1 sulfide or copper 2 sulfide. Either way, we are combining these elements together to make one new compound. All right, so there's some practice problems here. I'm not going to go through them. There's a video of me going through that. You can watch that afterwards. I'm going to keep on moving to talk about information. Next reaction type we have is decomposition. So in a decomposition reaction, you have one material and it's breaking down to make 2 or more different materials. Okay, so this could be, usually it's a compound breaking down, and it could be breaking down into the 2 elements that make it, or it could be a compound breaking down into just 2 simpler compounds. Either one. In the image that they show here, and again it might be a little bit hard to see, so we'll type it out. In the image here they have 2 HgOs. This is mercury oxide breaking down to make 2 Hg and O2. Okay, so we have mercury oxide breaking down into mercury and oxygen. Okay, so that would be a decomposition reaction. Let's take a look at another example. So decomposition reactions that produce gases and heat are sometimes explosive, as the photo here shows. Write a balanced equation for the following decomposition reaction. So they want us to write an equation for the decomposition reaction of hydrogen, of water, which is going to break apart into hydrogen and oxygen. Okay? So we're going to have H2O, which is a liquid. There we go. L. I keep having an S there. This is going to break apart into hydrogen gas, okay, which is diatomic. Remember, hydrogen is a Winkelhoff. And oxygen gas, which is also diatomic. Okay, so this is our equation. It does say to balance it. Oh, did we not balance the previous one? We did not. I just realized we didn't balance this. There should be a 2 there. The other one's balanced. My bad. Anyway, so we need to balance this. Balancing wise, we need 2 oxygens on the reactant side because we have 2 on the product side. And then we need to put a 2 there to balance out our hydrogens back again. So this is our decomposition reaction in this one. Okay. Again, we see a compound breaking apart into the 2 elements that make it up. All right. So again, the practice problems, you can go watch me do those ones. Let's keep on moving. Sorry, apologize. Next we have is a single replacement reaction. So in this kind of reaction, usually you're starting with an element, and it's going to react with a compound. Okay, and the element will replace one of the elements in the compound. Usually the element is going to be a metal, and so it's going to replace the cation that's in the compound. In the picture they show here, and again it might be a little bit small to see, but it's 2 potassiums, I guess, which is a solid, reacting with 2 H2O, which is a liquid. And then what's happening here is the potassium replaces the hydrogen. So we have potassium hydroxide as one compound, and this is aqueous. And then the hydrogen is by itself, and it is a gas. Okay. Now, H2O is sometimes better, instead of writing it as H2O, and I understand they wrote it as H2O in the picture. It's actually sometimes better to write it as HOH, okay, rather than H2O. Because if you look at it like this, it's basically hydrogen bonded with polyatomic ion hydroxide. So we can very clearly see that the potassium ion, or the potassium element here, is going to replace the hydrogen element. So that in our products, we have potassium bonded with hydroxide, which is where we get KOH from. And then the hydrogen is by itself. And then again, when it's by itself, it is diatomic. Okay. So you'll often see me in a lot of practice problems rewrite H2O as HOH because it's easier to kind of view and switch things around that way. All right. Now, one thing that we need to make note of here is when we are doing single replacement reactions, there is something that we need to use to determine whether or not these reactions will happen. And it's known as the activity series. Okay, so the activity series is a list of metals in order of reactivity, from most reactive at the top to least reactive at the bottom. Okay, and what this basically is saying, what this is for is, if the element, and this is actually really important, so I would very highly recommend that you listen to this part or write this down or something. Okay, so if the element that is by itself is higher on the list than the element that is in the compound, then a reaction will happen. If not, there will be no reaction. Okay, this is really important. So basically what this is saying is, if the element that is by itself in the reaction is higher than the element that is in the compound it's trying to replace, the reaction will happen. If not, nothing's going to happen. Okay, you would put these things together and it would just sit there and nothing would happen. So let's go look at the previous example here on this slide to see how this works. So the element by itself in this case was potassium. Okay, and the element it was trying to replace in the compound was hydrogen. So if we look on the reactivity series here, potassium, again, which was the element that was by itself, is higher on the list than the element that was in the compound, which is hydrogen. Therefore, the reaction happened and we had new products for them. okay? If it were the other way around, so let's say, for example, we had KOH here and H2, right? So we had hydrogen by itself with KOH. Nothing would have happened then, because in this case, hydrogen, which was the element by itself, is not higher on the list than potassium. Therefore, no reaction happens, okay? So there are some problems later on that you're going to be working on where it might say, like, you know, write out this reaction, or if no reaction happens, state no reaction. It's because of this, okay? So let's take a look at some examples here. We have two problems. So for each one, they want us to write the balanced chemical equation for each single replacement reaction, and they're telling us that they're taking place in aqueous solution. Sorry. Which doesn't really matter a whole lot. So, all right, so for letter A, we have zinc solid reacting with H2SO4, which is hydrochloric acid, that is aqueous. All right, so before we do this, we need to check our activity series. Okay, now one thing also about this activity series is it is on the back of your periodic table. So just to show you real quick, let me pull this up just to make sure that we know where it is. It's in the top left corner on the back of your periodic table. I'm going to pull one up here real quick just to make sure that we know where it is, because this is going to be very important for you to use for this chapter. Okay. All right, so let me just change my camera here real quick. There's me. Hi. And let's get our periodic table up. All right, there we go. So your reactivity or activity series is this upper left corner right here. Okay. So again, most reactive elements are at the top, least reactive are at the bottom. This is only used for single replacement reactions. Okay. Very important to know. So can we type on this? No. So we're just going to write single replacement only. Okay, this is for single replacement only, and you need to use this. So let's look back at our look back at our slides here, and let's take a look at this problem again. So we have zinc reacting with H2SO4. If this is single replacement, which it looks like, zinc would replace the hydrogen. Let's check on the activity series. Is zinc higher on the list than hydrogen? Yes. All right, so this reaction is going to happen, which means that in our products, we will have hydrogen by itself, and it is diatomic, so it's H2, and hydrogen is a gas at room temperature, so I'm going to write G to show it's a gas, plus H2 zinc sulfate. So the Zn is going to be paired with the sulfate ion. And I think it's aqueous. We actually can check we can check. I'm pretty sure it's aqueous though. Yeah. Yes, it is. Okay. Sorry, I'm just looking at my periodic table. So these are our products. Okay. Now, as to how I knew what the formula was going to be here. So remember that when these two things bond with each other, when the zinc bonds with the sulfate, okay, the zinc has a charge of 2+, and the sulfate has a charge of 2-. So those two things, charges are the same, so you need one of each to pair together. That's why there are no subscripts down here other than the 4, but that 4 is part of sulfate's formula, okay? So that's how I know it's SO4. And then we do need to balance this. And looking at it, actually, it's already balanced on its own. So we actually don't need to do any balancing. So, all right. For letter B, we have Cl2, aqueous, plus NaBr, which is aqueous. All right. Now, this one is a little bit weird because this is going to be single replacement. But in this case, we have a nonmetal replacing the nonmetal, right? Or an anion, because chlorine makes a negative ion, replacing the negative ion here. Whereas in the previous examples, it was always the positive metal replacing the other positive ion, okay? Now, if we look on the activity series, there is no chlorine, there's no bromine. So if you look at this, this isn't going to help you. And if we look on our periodic table, on our activity series on the back of our periodic table, there also is no chlorine and no bromine. So you might be asking, well, what do we do then? How are we going to determine whether this happens or not? So even though there's no activity series for nonmetals, there is a general rule of thumb. Okay, so elements that are higher up. So these are elements in column 7, but elements that are higher on the periodic table are more reactive than elements that are below them. Okay, so chlorine is higher on the list than bromine. Therefore, chlorine is more reactive than bromine is, and it will be able to replace the bromine in this reaction. So we're going to have bromine by itself, and bromine also is a Brinkelhoff. It's a liquid at room temperature, which doesn't matter. And we're going to have sodium chloride. Excuse me. We're going to have sodium chloride as one of our products. Okay. So in this case, again, the nonmetal replace the nonmetal. And then in terms of balancing, we need to have a 2 there and a 2 there. Okay. So this is our balance equation there. All right. We got 2 more reaction types to talk about. The next one here is double replacement. So this is going to involve an exchange of positive ions between 2 compounds. So this one, I kind of like to think of as like 2 people that are dancing, or like two couples that are dancing, and each like partner swaps with the other one. Okay. So in the little picture down below, and I know it's hard to see, we have K2Cl3 reacting with BaCl2. And they are making 2 KCl's and BaCl3, right? So this one, we have the potassium here switching with the barium. So in our products, potassium used to be bonded to carbonate, but now in our products, the potassium is instead bonded to the chlorine, okay? And likewise, the barium is bonded with the carbonate. So this is, again, we see that there's a swap. So these, this element here and this element here swap with each other. Oh, that's not what I meant to do. I meant to highlight that. There you go. Okay, so those 2 swap so that the carbonate and the chloride are then bonded with the other things. So this can be like dark blue, and then this can be like purple. Okay, so something like this. So now we have the potassium, which was the green one, bonded to the chlorine, which is the purple one. And we have the barium, which was like this turquoise teal looking color. And that one is bonded to the carbonate, which is the dark blue. Okay, so we just see that they swap. Pretty simple. The main thing is that when they swap, you do have to rewrite the chemical formulas, and you have to remember the charges. Okay. So I'll show you what I'm talking about here in this example. So they want us to write the balanced chemical equation for each of these double replacement reactions. So it's going to make a text box here. And let's make our font the right size. All right, so for A, we have calcium bromide. Okay, so CaBr2 aqueous plus AgNO3 also aqueous. And it tells us, I apologize for all the yawning. It's been a long day. It tells us that we make a precipitate of silver bromide. All right, so in these double replacement reactions, we are going to have to use another thing on the back of our periodic table called a solubility table. Okay, so what we're going to do is we're going to write out both products. And then we need to check to see if one of them is a solid. Now, it does tell us here that one of them is going to be a precipitate, and that is a fancy word of saying one of them is a solid. But we're going to check anyway. Okay, so first let's just write out our formulas, and then we'll show you how we check stuff. So double replacement means the calcium and the silver are going to switch. So the calcium, Ca, is going to bond with the nitrate, okay, the NO3. So NO3. And I'm going to talk here how I get this formula, okay? So just bear with me. Let me write out the other one, and then I will talk about how I got these formulas. All right, so remember that bonded up. Okay, so the calcium bromide, we have calcium, which has a charge of 2 plus, bonded with bromine, which is 2 minus, or I'm sorry, minus 1. So we have a -1 charge ion and a +2 charge ion. We need 2 bromides to balance it out. That's why there's a 2 in the formula here. Okay. As for the other one, we have silver, which is Ag. That has a charge of +1, bonded with nitrate, which is -1. Okay, +1, -1, those balance out. That's why there's no subscripts here. However, when these ions switch and the calcium is now bonded with the nitrate, we have to rewrite our chemical formulas. So now that the calcium bonds with the nitrate, calcium is again 2 plus, nitrate is -1, so we need 2 nitrates to balance out the calcium. That's why there's a 2 here outside parentheses. Okay? And with the other one, silver is +1 and bromine is -1. So those two would balance each other out, and therefore there's no subscripts. Okay, so understand that like when we have double replacement, these little numbers, like this little 2 here, does not go with. This 3, however, that does go with, because that is part of nitrate's formula. Nitrate is NO3. Okay, that's like part of who it is. But there's no other numbers. Okay, so this is our chemical equation. We have to balance it because it's not balanced. So if we look at calcium, we have 1 calcium on the reactant side, 1 calcium on the product side. That's good. We have 2 bromides on the reactant side, only 1 bromide on the product side. So we're going to put a 2 there to give us 2 bromides. That's also going to give us 2 silvers. On the reactant side, we only have 1. So we're going to put a 2 there to give us 2 silvers. And then that also gives us 2 nitrates. But fortunately, we had 2 nitrates right there on the product side. So that is our balanced chemical equation. And from here, then, the last part is we need to check which one of these will be a solid. Okay, so to do that, again, we're going to look on our periodic table. And in the upper right-hand corner on the back, there's this big chart. Okay, there's this big chart here. This is called a solubility table. So what it does is it tells you if a compound is going to be soluble in water. That means, like, does it dissolve in water? In order for our double replacement reactions to happen, one of the products we form has to be a solid. Okay? If both of them are not solid, so they're both aqueous, as many of these say, they say AQ. AQ stands for aqueous. That means that it would dissolve in water. If both products are aqueous, then no reaction will happen, in which case you probably wasted a bunch of time writing on a chemical equation for a reaction that doesn't happen anyway. Okay, so let's go take a look at our products again. So this is right over here. This is calcium nitrate. This is our solubility table. Okay, we have calcium here, we have nitrate here, and if we find each of them and we line them up, we'll see that this says aqueous. So that means that our product for calcium nitrate is going to be not soluble, so AQ. All right, so that's not good. That means that this other one, which is silver bromide, hopefully is a solid. So let's go check that one. Okay, so let's go check silver bromide. So we have silver. Let's erase these real quick. So we have silver, which is here, and bromide, which is here. And these, when we line them up, says S for solid. All right, so that's good. That means that this will make a precipitate, it will make a solid, and this reaction will happen. So back on our notes, we'll write S for solid, and that one is the one that we're looking for. Okay, so that is our final reaction written out like that.